What is the latent knowledge estimation problem addressed in the paper?
The latent knowledge estimation problem addressed in the paper is how to determine whether a given language model, LLM, has latent knowledge of facts about real-world entities, such as knowing that Albert Einstein was born in 1879. The paper focuses on estimating the extent to which factual knowledge about real-world entities is embedded in LLMs by leveraging in-context learning, ICL, to probe the LLM and evaluate its responses in a way that aligns with the design principles set in the paper. The goal is to develop a reliable latent knowledge estimator, LKE, that can accurately assess the factual knowledge stored in LLMs without relying on traditional prompting methods that are prone to prompt engineering and prompt hacking issues. The paper proposes a novel approach that uses in-context examples to communicate information about relationships between subjects and objects to the LLM, allowing for a more robust and reliable estimation of latent knowledge in LLMs.
How does the proposed in-context learning-based LKE work, and how is it different from prompt-based approaches?
The proposed in-context learning-based latent knowledge estimator, IC-ELK, works by leveraging in-context learning capabilities of large language models, LLMs, to estimate whether an LLM knows a specific fact. It constructs prompts by providing a list of facts related to the given fact, allowing the model to infer the relationship between the subject and object without explicit instructions. The IC-ELK prompts the LLM with in-context examples based on the relationship type, enabling the model to extrapolate patterns and retrieve the correct answer. The model's output probabilities for the tokens of the correct object are compared to alternative objects to determine if the LLM knows the fact. This approach is different from prompt-based methods, as it avoids prompt engineering and reliance on meta-linguistic judgments. IC-ELK uses a minimalistic prompt design based on in-context learning across all relations, making it more flexible and effective in estimating latent knowledge compared to traditional prompting techniques.
What are the advantages of using in-context learning for knowledge estimation over traditional prompt-based methods?
The advantages of using in-context learning for knowledge estimation over traditional prompt-based methods are as follows. 1. Reliability. In-context learning helps to address reliability concerns associated with prompt-based methods by avoiding prompt engineering biases and reducing the potential for prompt hacking. This ensures more trustworthy and accurate estimates of latent knowledge in LLMs. 2. Simplicity. In-context learning offers a simple and straightforward approach to estimating latent knowledge without the need for complex prompt designs or extensive prompt engineering efforts. This simplicity makes the method more accessible and easier to apply across different LLMs and knowledge bases. 3. Flexibility. In-context learning is flexible and can be applied universally to test factual knowledge of relations across a variety of structured knowledge bases and LLMs. It does not require relationship-specific or LLM-specific prompt engineering, making it adaptable to different contexts and tasks. 4. Efficiency. In-context learning leverages the in-context learning capabilities of LLMs to efficiently communicate information about relations without additional instructions. This efficiency allows for the extraction of factual knowledge with minimal effort and resources. 5. Generalizability. In-context learning can be broadly applied to any kind of LLM without making assumptions about how the LLM outputs text. This generalizability enables the method to be used across various LLM architectures and training datasets. 6. Higher performance. Empirical findings show that in-context learning outperforms traditional prompt-based methods in terms of higher mean accuracy and lower standard deviation, indicating a more consistent and effective approach to knowledge estimation in LLMs. In summary, in-context learning offers advantages such as reliability, simplicity, flexibility, efficiency, generalizability, and higher performance compared to traditional prompt-based methods for estimating latent factual knowledge in large language models.
How are the alternative facts generated for the multiple choice testing in the proposed method?
In the proposed method, the alternative facts for multiple choice testing are generated by selecting alternative objects from other facts in the dataset that share the same relationship type as the given fact. Specifically, for each fact in SureMath X, in SureMath R, in SureMath Y***, a set of alternative objects in SureMath A Y is created by collecting tail entities from other facts with the same relationship type as the given fact. This process ensures that the alternative objects in SureMath A Y are viable choices and cannot be easily eliminated. The number of alternative objects sampled per fact is set to 99 for computational feasibility, ensuring that a random guess between the correct object and the alternatives has a 0.01 probability of being correct. This method allows for a diverse set of plausible alternatives to be considered for each fact, enhancing the robustness and effectiveness of the multiple choice testing approach in estimating the latent factual knowledge of the language models.
What are the main findings regarding the knowledge estimation performance of different LLM families and sizes?
The main findings regarding the knowledge estimation performance of different LLM families and sizes are as follows. 1. Some model families, such as Mistral, Llama 2, Gemma, and Llama, consistently demonstrate higher factual knowledge performance across various relations compared to Pythia, Bloom, and Opt families, indicating varying levels of knowledge across different model families. 2. Larger models within each family generally outperform their smaller counterparts in terms of accuracy, suggesting that larger models tend to capture a broader set of facts due to their increased capacity. 3. Despite models within the same family being trained on the same datasets, there are differences in the specific facts they retain from their training data, indicating that models within the same family may remember different sets of facts. 4. The subsumption rate analysis between pre-trained and fine-tuned models reveals that fine-tuned models may not be acquiring additional knowledge beyond what is already present in the base models, suggesting that fine-tuning may reduce the amount of extractable latent knowledge in the models. Overall, the study highlights the variations in knowledge levels across different LLM families and sizes, shedding light on how model architecture, training data, and fine-tuning impact the factual knowledge embedded in LLMs.
What are the limitations highlighted in the paper regarding the proposed in-context learning-based latent knowledge estimation approach?
The limitations highlighted in the paper regarding the proposed in-context learning-based latent knowledge estimation approach include biases introduced by the selection and formulation of in-context examples. The choice of which examples to include, their order, and their factual accuracy can influence model responses, requiring careful curation of in-context examples for reliable latent knowledge estimation. Additionally, the study's limitation in testing simple format facts underscores a gap in assessing LLM's complex reasoning abilities. The framework predominantly focuses on the LLM's ability to recall or recognize factual information from structured prompts, limiting the evaluation to straightforward factual recall and overlooking the model's capacity for more advanced cognitive processes like reasoning, synthesis, and inference.